Hi, I'm Jon Higgs. I'm an SRE at Redbubble. Redbubble is a marketplace that allows independent artists to sell their artwork on physical products like t-shirts and jumpers and phone cases and posters and all sorts of things. Today I'd like to talk about Red at the Edge, measuring the performance and reliability of your HTTP services. This journey for us began 3 or 4 years ago when we introduced Kubernetes into our ecosystem. Kubernetes, that allowed us to divide our monolith up into many different services. Each time we did that, we created a new dashboard for the new service. And over time, as the monolith got divided more and more times, we stopped having an overall view of the performance of our service. We could see the performance of one slice, each service individually, but we lost that high level view of what are our customers experiencing, what kind of service level are we're delivering. I thought about this problem around March 2019. It's a fairly well-known problem. Google, they have solved it with 4 golden signals, and the red metrics, that's a derivative of that system that's more applicable to HTTP services. What it says is that to get a strong signal of the health of a service, you can measure 3 things. You can measure the rate of requests going to it, the amount of errors that are coming from it, and the duration for each response to be returned. Now, those 3 things will give you a strong indication if the service is not performing well or is broken. So I thought about this. All of that information can come from HTTP access logs. One request generates 1 log. So we know how many requests come through just by looking at the count of log lines. We know whether or not a response was an error. So if the HTTP status code was 500, then it means that the service failed to deliver a response. And most importantly, it differentiates why a failure occurred. Was it a failure on our part, or was it a failure on the requester's part? Like, was the request malformed, or did we fail to be able to generate a response for other reasons? So that gives us a really good indicator of errors that are actionable by us. And the access logs also contain the backend response time from the load balancer. We can measure access logs from our load balancers. Anything that serves HTTP can pretty well emit an HTTP access log. So with a few implementations, we can measure many systems that are behind our network. So our architecture looks a bit like this. We have users that make requests to Cloudflare. Cloudflare modifies the host header so that after it passes an external ALB, which is the way into our Kubernetes cluster, the Kubernetes ingress controller is able to use the host header to route to the correct the correct application pod. Internally, so this turned out to be not exactly a good pattern for us, but what it did do was provide one single point where we could measure all traffic that goes across our internal network. So for a pod to make a request to another pod, it leaves the cluster, goes to an internal ALB, and then enters the cluster again. That's a whole different topic as to why that's not a good pattern, but for measuring red, it made it very easy. How it works. So in order to be able to measure HTTP access logs, there's a few things you need to know. You need to know when there are logs available to be processed. and you need a processor to be able to process them. So we do this by, we know when logs are ready by dropping an event into an SQS queue. Now there's a couple of different ways that we can do that. We have one way for ALBs, application load balancers, and we have another way for Cloudflare. Then we have workers that they pick a message off the queue, pull the log data for that message, extract metrics from the logs within the data, and then publish the logs to Datadog. Datadog is the presentation, I suppose. We use that to generate our dashboards and view what is happening in our environment. We can also drive SLOs from that data, or metrics for that matter. So the ALB events, an ALB is a cluster of nodes, load balancer nodes, and each node, if the cluster is configured to publish metrics can be configured to publish metrics to an S3 bucket, and each node will flush its logs every 5 minutes to that bucket. S3 has a feature of being able to publish, if you publish a file to an S3 bucket, a create object event can be emitted, and you can hook into that event and use it to place the metadata for the file that was created into an SQS queue. And that's what we do. Cloudflare events are slightly different. Cloudflare doesn't publish its logs to an S3 bucket, but it does make the logs available via an API call. What we do is we schedule an event so that every minute the epoch for now gets placed into an SQS queue with a visibility delay, so that when the worker is able to see the message and retrieve it from the queue, the API has had time to make the logs available. There is a slight delay between for Cloudflare to make the logs available via the API. It's about 5 minutes. So we need to wait for that. The processes work pretty well the same between the two. You have a processor, it picks up a message from the queue, it uses the data within the message to know how to get the logs. Once it has the logs, then it minifies it, reduces it down to the bare minimum. So with ALBs in particular, you'll get a bit of noise there for requests that aren't to your application. With host headers that aren't yours at all. You don't want to be publishing events for other people's data because you're paying for them, and it adds noise to your dashboards, not to your dashboards, to when you're searching for metrics. So once your data is minified, also you pull out any columns that aren't needed, like say host header, for example, not host header, say user agent, for example. You group the logs. We group them by host header and by minute. And for each group, we calculate the aggregates. The aggregates are two classes. One is the request, a count of requests with a few tags. One of the tags is the response status, whether it was a 200, 300, 400, or 500. Just the entire class, not the individual status codes within them, because that will generate too many metrics. And it isn't useful enough. And the second thing is the duration at various percentiles. So grab all of the logs and then find the P50 and publish that, P90, P95, maybe P100. So publish all of that data to Datadog as an aggregate, and then it becomes available to your dashboards. You can make something like this. So this is the dashboard for Cloudflare. You can see that the request rate there's two charts in that graph. One is for the amount of user requests and the other is for the amount of search engine requests. We can differentiate those two based on a field that's in the Cloudflare logs. And we can see then the error rate, the percentage of requests that were a 500 class. And then after that, the duration at those percentiles. You can see any changes there over time. We have a very similar dashboard for our internal ALB. Again, the request rate, the error percentage, and the duration. We can slice this down per application as well. The data that's published is given a tag for the backend host header. So what we can see here is the request rate for an application named shop, the error percentage, and right there, there's in the middle of the graph at around midday, you can see that there is a spike in errors. And that corresponds quite closely to some red bars, which denote when deployment events completed. So what you might be able to infer from this data is perhaps shop isn't exactly zero downtime. Sometimes. Often it is. I haven't looked into this. I'm not actually sure. It could be unrelated, but that's the kind of information you can get from this. As well, when you look at all of the different applications, what you sometimes see is that there's a correlation between unrelated applications experiencing errors. You can use that to infer that maybe there's a platform issue. These applications are unlikely to fail simultaneously. It's more likely that there's something common to them all, which is often the platform. So that kind of information is fairly invisible if dashboards are all over the place and there's some inconsistency between them as well, like the data is incomparable. So how did it go? We have standard data, comparable data that measures every request that crosses our network or enters our network. New backends, no configuration are needed to set up a new backend. This data is extracted automatically via the data that's contained within the log files, and new metrics are published for anything that's there, so long as it wasn't minified out. And we're taking measurements for Cloudflare at the CDN. So if you were to increase the hit rate for your application, the cache hit rate, then these requests, they become measurable. If you were to do that while taking the measurements from the application itself, what you would see is a reduction in the number of requests going to the backend because they're served directly from cache at the CDN. Instead, when looking at the logs at the CDN, you can measure all of these requests that are cache hits, so you know whether or not there's a reduction. And the duration for those requests, you'll have requests that have a backend duration of 0. There was no backend time because it didn't go to the backend. That can be really helpful for driving SLOs and understanding what is the user experiencing. If you completely ignore all cache hits, then there's little incentive to improve the hit rate, for one. But yeah, you just, by measuring it, you have a much better understanding of what's happening in your environment, and that is valuable. And backends, they're not measuring themselves. If a backend goes away and can't receive requests, and therefore can't measure requests, then there's a whole class of errors that go completely undetected. The class where requests were unable to be routed to your application, and that can sometimes be significant. If you were to set this up yourself, there's a few considerations that you might want to think about. One is that you're relying a lot on HTTP status codes, and they should be accurate. If a malformed request can cause your application to explode because it can't handle that and return a 500 instead of the proper 400, then that's going to distort your view of your error rate. Often, like if you have people trying to scrape your site for things or just probe, it's not uncommon to have a lot of requests, especially in a short period of time, a lot of requests that are all malformed, just trying to see what happens. Really, ignoring 400s is the best way that I've come up with how to handle that, so that your errors are true. So if your application is exploding and returning a 500 when that happens, then yeah, it becomes a little bit hard. You get these false alarms in your data. By using events, you are able to populate your SQS queues without any compute at all. There's AWS has a lot a lot of points where you can emit events. S3 is one, but there's a few others as well. A lot of others now. So you can do that all without any compute at all. Really simple. There's no possibility for a failure due to your system breaking. You've got fewer moving parts. StatsD, that's a really easy way to publish metrics, except it's not appropriate for this because we're processing historic data, and we need to apply a timestamp to that. StatsD has no provision for setting a timestamp, so it can't work. We use the Datadog API instead. And Datadog histograms, they're pretty good at doing things like measuring the P50s and whatnot, like the data at various percentiles. But that means that you need to send every single request going through, and with our volume, that didn't really seem appropriate. And also, I don't know how well it would handle reprocessing historic data, like replaying data from, like if you fall behind on your queue, or if you're processing messages out of order, which is what's going to happen with the standard SQS queue. You need a FIFO queue if you need it to process in order, and then you lose your concurrency. So some statistics for our particular implementation. We process 170 million requests an hour, and we publish 4,700 metrics from that data. That provides data for 120 backends. We have a 15-minute delay for the data out of Cloudflare. That's mostly due to having to wait a bunch of time. I think that's about 8 minutes or so for the data to become available, just to be absolutely certain that it will be there. If a retry happens, then yeah, you're going to sort of double that processing time for that data. And there's an 8-minute delay for ALB metrics. You need to wait 5 minutes for the logs to flush. Our 10 workers to keep up with this request volume costs $300 a month. The workers are mostly implemented with awk, and they're glued with some shell. That was chosen because it's really, really fast and it uses few resources. It works pretty well, and yeah, it could be optimized further perhaps, but it's good enough for now. Thank you. I hope this presentation has been helpful to you. I am happy to answer any questions if you have any via email. And I'm also interested if you have implemented something similar yourself and done it differently. There's a lot of different ways that this could be achieved, and what I've shown is by no means the only right way. There could be plenty. Thank you.